I am going to present the algorithm we designed to publish a number of works and the Katz centrality under local differential privacy. So first I'm going to introduce the motivation behind our work. Differential privacy is the idea that when you publish some statistics or data or property which depends on the whole topology of the graph, you might leak some information about the presence or absence of an edge between two particular nodes. And since we don't want this information to be leaked because it can be private and sensitive, instead of publishing the data that we want to compute, we are going to publish some random estimate of this data. And this random estimate is going to be computed in a way that from the result of this estimate, it's not going to be possible to gain information about the presence of or absence of an edge between two nodes. During our work, we were working under local differential privacy, which means that we have the additional constraint that we don't trust a central server to store all of the data of our graph, meaning all of the edges. And so our algorithm needs to be decentralized, which means that each node is going to run some algorithm, but when it has only access to its own neighbors, it doesn't have access to other edges in the graph. And then it's going to publish its results, but when it has been randomized, and so therefore protected from a differential privacy point of view. And it's going to send this data to a central server, which can then do some computation with the data because it's already protected from a differential privacy point of view. And so even the central server cannot have access to the particular edges of our graph. So now let's define what is the number of walks and Katz centrality and how they relate to each other. So the number of walk pk of v is the number of walks of length k which starts from node v. And given this definition, we can define Katz centrality. So the Katz centrality of node v is given by taking the sum over all integer k of the number of walks of length k which start from this node v, and you add some attenuation factor alpha to the power of k, which ensures that the sum converges. And so we see that if a node is connected to a lot of other nodes which are themselves very connected, then this node is going to be central. And so that's a good metric of the centrality of a node within a graph. Now let's introduce the precise mathematical definition of local differential privacy. So a local randomized algorithm RV, which takes as input only the list of neighbors of V, is said to protect epsilon local differential privacy if for any possible range of output of this algorithm V, if you take two lists of neighbors which differ only by 1 bit, then the probability that this random algorithm, when it is running on one of the lists, fall into the range S, is very close to the probability that the same random algorithm, when it is running on the other list, also falls on the range S. And so the idea is that if you have an observer which is looking at the output of the random algorithm RV, which is trying to tell apart what was the ground truth, so was it the first list or the second list when they differ only by 1 bit. While this observer, because the algorithm are randomized, is going to be forced to do some probabilistic inference to gain information about the ground truth, but because, and is going to do so using Bayes rules, but because the probability are so close to each other, the amount of information that the observer is going to gain is very limited. Now let's introduce sensitivity and the Laplace mechanism, which is a mechanism used to turn a deterministic local algorithm into a randomized local algorithm which protects epsilon local differential privacy. So first, the sensitivity sigma of a deterministic algorithm RV is the maximum amount the output of the algorithm can vary when you flip 1 bit of its input. So its input again is the list of neighbors. And so given this deterministic algorithm of sensitivity sigma, you can build a local randomized algorithm which is going to protect epsilon local differential privacy by adding a Laplacian noise of scale sigma over epsilon. So now that we have all the necessary notion to understand our work, let's introduce the algorithm. So the idea behind our algorithm is to notice the relationship between the number of walks of length k and the number of walks of length k minus 1. And this relationship is that the number of walks of length k starting from node v is the sum over all of its neighbors of the number of walks on length k minus 1 starting from the neighbor. So the idea is that to have a walk of length k, the first step of the walk is going, if it starts from node v, it's going to necessarily go to one of its neighbors of node v, and then you have k minus 1 in other steps, and so that's why you add the number of walks on length k minus 1 for each neighbor. And what we can notice is that this recursive relationship has a sensitivity sigma, which is the maximum of all nodes of the graph of the number of walks of length k minus 1. And so we have a deterministic algorithm with some sensitivities that we know. We are then going to be able to use this relationship to build a randomized algorithm which protects epsilon local differential privacy by recursively computing estimates of the number of walks of length k. Now, when we were designing this algorithm, we noticed that sometimes the sensitivity of our algorithm can be very large, and that's why we have introduced a clipping mechanism which forces the estimation of the number of walks of length k to be in the range minus x to the power of k and x to the power of k, which means that our estimate is going to stay relatively small, and therefore the sensitivity and finally the variance of our algorithm is going to stay small. And here the number x is some clipping factors that we can choose at the beginning of our algorithm. And we can see that if we choose a very small values of x, then we are going to have a very small variance, but we are going to introduce a significant bias because we are cutting the values of estimate at each step at x to the power of k, which is a small value if we have chosen a small value for x. So finally, to summarize our algorithm, we choose a number of steps s that we want to run, and then at each step we compute pi, which is the scale of the Laplacian noise, and which is going to be proportional to the maximum value of all nodes of the graph of our estimates of the number of walks of length k minus 1. Then, given the recursive relationship that I introduced earlier, we compute the estimates of number of walks of length k, and we don't forget to add some Laplacian noise to make sure that this computation is protected from a local differential point of view, and that we can therefore publish this information. Now that we have this, we can update our estimate of Katz centrality. When we see the definition, we notice that we should go all the way to infinity, but to have our algorithm run in a finite time, we choose to stop at a given step s. But otherwise, it's the exact same computation, except that we use estimation of the number of walks instead of the actual number of walks. And finally, we use some clipping mechanism at the end of step s to ensure that, at the end of step k, to ensure that at step k plus 1, the sensitivity is going to stay relatively small. We have managed to prove some theoretical results that whereas the proof was too long to include in this presentation. But to summarize, we prove that for a sparse enough network and for small enough values of alpha, we show an upper bound for both the bias and the standard deviation of our estimators, and both are proportional to alpha times the number of steps divided by epsilon, the privacy budget. And finally, we can also show the experimental results, which are particularly interesting because we have run our experimental results for some graph which didn't follow the assumptions that we made for our theoretical results, meaning that our algorithm has good behavior even beyond what we have proven. And so we ran our experimental results on two graphs, one being a subgraph of Facebook and another being a subgraph of Wikipedia. In both, of course, the nodes were anonymized. In this experiment, the curve in blue represents the algorithm that we have introduced, and we have compared it to the most naive algorithm possible, which is the randomized algorithm, meaning that we are just going to run a simple algorithm where we do the regular computation, but at the very first step we randomize the whole graph by flipping each edge with some given probability. This ensures that differential privacy is preserved no matter what kind of computation you do afterwards, and so then after you just do the regular deterministic computation as if you had the real graph. As we can see on all the pictures is that our algorithm greatly outperforms this simple naive randomized algorithm. So if we go at the figures on the upper left, we have the variance, which is the dotted line, and the loss, which is the squared line. So the loss is the squared loss of our estimator. And this is given when we change the number of steps. And what we can see is that the variance is increasing when we add more steps, which is not very surprising because at each step we add some noise, and also the noise is proportional to the number of steps that we have. And we also see that the bias squared, which is the difference between the square loss and the variance, is reducing as we increase the number of steps. This is because the real definition of Katz centrality would be to go all the way to infinity during our calculation, but because we stop at some step s, we introduce some significant bias, and so when we increase this number of step s, we are getting closer and closer from the ground truth, and hence we are reducing the bias. And so we can see something very similar on the upper right figure for the loss and variance for the Wikipedia graph. But on this specific figure, we can see that the randomized algorithm performed much worse with some exponential growth given the number of steps s. Even though this is interesting result, it's not clear that the loss and variance of our estimator are very useful metrics, because usually the Katz centrality is used to rank the nodes to know which are the most important and which are the less important. We thought that a good metric would be to measure whether or not we were able to come up with the same ranking based on our estimation of Katz centrality. And so that's the figures on the middle left and middle right. Shows you the proportion of nodes from both the top 10 and the top 100 nodes that we were able to recover based on our estimation. And so, for example, if we take the Facebook graph, we saw that we were able to recover almost 80% of the top 10 nodes, so 8 out of 10, and about 90% of the top 100 nodes. So that's using our clipping algorithm, and we got a much more poorer performance using the randomized algorithm, of course. And we have similar results for the Wikipedia graph. Finally, something else that we can do is, instead of changing the number of steps, is to change the clipping factor. And so that's the last two figures of this poster. So on the bottom left, we have the variance and loss of our algorithm for various for different values of clipping factor. And on the bottom right, we have the detection rate for various values of the clipping factor. So what we can see, and this is something that we also saw during our theoretical results, is that there is some middle ground to be found for your clipping factor. Because if you have a very small clipping factor, like I said earlier, then you are going to clip very often your estimation of number of walks of length k. So you are going to achieve a very small variance, but at the cost of having a very big bias. On the other hand, if you take a very large clipping factor, then you are going to have to be able to achieve a very small bias, but this is going to be at the cost of not controlling the sensitivity anymore, and therefore having possibly a very big variance. This is why the optimal solution is to find a middle ground between too small and too large values of clipping factor. Finally, what we can see on all the experimental results by comparing the loss and variance and the detection rate is that you can achieve a very good detection rate as long as you keep the variance small, even if you have very large bias. And that is because it's possible that the bias is the same for most of the nodes, meaning that it's not going to affect too much the ranking of the nodes, which is what matters for the detection rate.